Okay, so now the part that requires a little bit more work is just going to be computing this limit, right? As I take time to 0. So that's the third property. And in order to show that, right, that this is equal to g of x0, okay, let's start by fixing some x that lives in R. I'm going to fix some epsilon greater than 0, okay, and I'm going to choose, okay, some, I'll call it gamma. I think I have delta in the written notes, but I'm already using delta, okay. I'm going to choose these such that, that's my little such that symbol there, g of y minus g of x0 is bounded from above by epsilon over 2, okay, if y minus x0 is less than gamma, okay? And why can I do that? I can do that because g is continuous, right? I can use this sort of, epsilon delta bounding, basically for y living in R, okay? Well then, if I do that, then what I can say is that u of xt, okay, minus g of x0 is equal to what? Well, just plug in the formula that I have. And that's going to be phi of x minus yt, okay? And because phi integrates to 1, right, I can treat this term as the integral over phi multiplied by this. It's just like multiplying through by 1. So I'm going to get a g of y, and then I'm going to pull in the g of 0 into this integral, okay? Basically because the integral, right, of phi is equal to 1, okay? That's what was involved in that step. Using the definition of u, and then using the fact that phi integrates to 1, okay? So this is going to be bounded from above by the contribution from right around the spot where this is going to blow up at t equals 0, where x and y are equal to each other, and then every other part of the domain. So I'm going to split it up based on that. You see it's bounded from above by the part of the domain that's close to x0. So phi of x minus yt, g of y minus g of x0 dy plus the rest of the domain. So wherever y minus x0 is greater than delta, phi of x minus yt, g of y minus g of x0 dy, okay? And this essentially is an application of the triangle inequality, okay, and integrability, right? All right, so I'm going to call these two things, I'm going to call this thing I, and I'm going to call this whole thing here J, okay? And I'm going to split these up, and now I have to go to work to bound these things I and J, okay? So first of all, okay, our choice of gamma here is going to imply that I is bounded from above by epsilon over 2, the integral over the real line, phi of x minus yt dy, which I know that whole thing integrates to 1, so it's just going to be bounded by epsilon over 2, okay? remember what I said at the beginning, this thing is going to be no bigger than epsilon over 2. So we're using that now, okay? And then I'm only integrating over a subset of the domain, so it should definitely be bounded from above by the integral over the whole domain, okay? If I take the integral of phi over the whole domain now, so I can bound I in that way, okay? The J part is what's hard, right? So let's go ahead and do that. So second, okay, and assuming that x minus x0 is less than or equal to gamma over 2, and y is minus x0 is greater than or equal to gamma, okay, then I can do the following, okay? I can write y minus x0 is bounded from above by y minus x plus x minus x0, okay? This is bounded from above by y minus x plus gamma over 2. This is bounded from above by y minus x plus 1/2 y minus x 0, okay? And so this implies that 1/2 of y minus x0 is bounded from above by y minus x, okay? Now, why do I need that, okay? Well, to help me bound my integral j, okay? So my integral j is going to be bounded from above by 2 times just the maximum value of g. So remember my integral j was here, right? And it involves the largest that g ever gets in this case, okay? So so I can say, well, you know, however big this is and however big this is, that difference can be no bigger than twice the maximum of g, okay? So that's where that term comes from, okay? And then what remains now is just this integral, right? So y minus x greater than delta phi of x minus yt dy, okay? And this is equal to basically the constants that's involved in the scaling of my Gaussian, right? The 1 over square root of 4 pi k part. I'm just going to lump that together with the 2 and call it c. I'm going to save the square root of t part from that. And I'm going to just plug in the definition of my phi there. Okay, so that's just my phi. And now what I have to do with this part, right, is to figure out how to bound it, okay? I want to make sure that I have lined up the peak, okay? So it is outside the range of integration, okay? So that's why I cut away the part that's close to x equals x0, because as I take the limit as t goes to 0, I'm going to have a singularity there, okay? And I've already kind of dealt with that singularity in the integral I. So kind of what I have in this integral now should be outside of that singularity. Okay, so I should get something that's bounded. okay? So how do I show that, right? So I write that now J is less than or equal to C G integral or the maximum value of G, right? The norm of that. This integral is taken now from y minus x0 is greater than delta. I'm going to now make a subtle change in the argument of my Gaussian using the identity that I applied before, right? So you see here now I have y minus x0 rather than y minus x. And I essentially used this identity that I derived before, right? That y minus x squared is greater than or equal to a fourth y minus x0 squared. And so I can do a quick change of variables to essentially write this as the integral from, sorry, somehow along the way I started writing this as, I want to make sure that you know that that's gamma, not a delta there. My gammas are starting to look like deltas. Okay, this integral should go from gamma up to infinity, e to the minus c squared 16 kt dz, where I've basically taken y is equal to, or sorry, yeah, z is equal to, oh yeah, so where z is equal to y minus x0. And now if I take another change of variables, okay, and we'll call it v is equal to z over 4 times the square root of kt, and I get that dz is equal to 4 times the square root of kt dv. What I get from that change of variables is, again, just a integral that's over a much cleaner integrand. So essentially that j is bounded from above now by some constant. The integral from gamma over 4 times the square root of kt up to infinity, e to the minus v squared dv. Okay. And as t goes to 0 from above, right? What I should have is that this vanishes, okay? As t goes to 0 from above, right? My limit of integration is going to blow up to infinity, okay? And so this whole integral should vanish. I can show that now, okay, by saying that j is going to go to 0 as t goes to 0 from above, okay? Basically because the integral from gamma, excuse me, over 4 square root of kt up to infinity of e to the minus v squared dv, okay? This is going to be equal to 1 minus the error function gamma over 4 times the square root of kt. And this is equal to, yeah, so this is basically gonna, for t small enough, is less than or equal to epsilon over 2, okay? So as long as x minus x0 is less than gamma over 2, okay? In other words, t greater than 0 is small enough, then u of xt minus g of x0 is less than some epsilon, okay? So for whatever epsilon I like, I can make this difference less than epsilon. So that's the same as saying that u of xt limits to g of x0 as long as I'm taking t close enough to 0 and x close enough to x0. Okay, so that's property 3. Took a little bit more work. I'm going to pause now. Are there questions or comments about this part?